Welcome back. I want to take a quick section to cover a topic that is often forgot about in data science and machine learning courses. However, in order to truly understand a topic, we need to understand the high-level principles and the landscape of that topic. In this case, we want to work as a data scientist or a machine learning engineer, so we need to at least understand the topic of data engineering. But what does that mean? What's with all these titles? Data scientist, data analyst, data visualization. This is madness. This is so confusing. Well, let's talk about data engineering and how it fits into this whole ecosystem that we've been talking about up until now. Now, we learned that data science is all about using data to make business decisions, right? One of the ways that we can make business decisions is to use a technique like machine learning that allows a computer to learn and figure out the solution to a problem that may be a little too complicated for a human to solve or maybe too tedious and takes too long of a time. So we want to automate it. So machine learning is a technique and data science is the idea of using data and converting it into something useful for a product or business. And data analysis is a subset of data science that allows us to analyze the data that we have. But the missing piece is that of data engineering. And not all companies have data engineers, but as companies get bigger and bigger, they need to hire for this role. Let's take a look at why. Who brings all this data to us in a nice little file? Where is this data coming from? How do we manage it? Do we throw it out after we're done? Who labeled this data? You see, a data scientist or a machine learning expert doesn't need to concern themselves, most of the time, with these topics. You ideally have the data accessible to you because this part of data is handled by a data engineer. So who is this mythical figure? Well, a data engineer would take all of the data points that are incoming. Let's say for a company, let's say this company has all these products and all these data are coming from their users, from their security cameras, from their website, from IoT devices. And a data engineer takes all this information and then produces it and maintains it in databases or in certain type of computers so that the business has access to this data in an organized fashion. So they're kind of like the librarians where they collect all this information and they organize it for us so that people like machine learning or data science experts can use this data. But this is a simplified version of what a data engineer does. In order for us to really understand this, we need to go back to the beginning and ask the question, what is data? I'll see you in the next one. Bye-bye. Welcome back. So what is data? I mean, we've talked about it already, and we should have an idea of what data is. And we also know why business care about data, right? We live in a world now where data is valuable. And some of the most valuable companies are valuable because they collect data. Companies like Facebook and Google sell data to make money. They provide products for customers by using the data to improve their products. Data is the new gold. So businesses care because by understanding their data, it could be part of the product, such as creating a YouTube recommendation engine. We can ask if the company is doing okay to monitor the company's sales and statistics. And you can also use data to improve the company and ask, can we do better? What can we improve on? How can we make our apps faster? So businesses care a lot about data. But I want to take a bit of time to really understand what data engineers do by manipulating or collecting this data. So let's talk about the 4 different types of data. We learned that there's things called structured data. Now, this is data that is actually organized well for us to understand and read. because data gets collected in different ways from different sources, right? But once on a computer, there's a standard way, usually in a table or what we call a matrix, a table that makes it easy to read. Attributes are usually columns, and rows are usually instances. And sometimes we have the outputs in the rightmost column, like we saw with machine learning, where we predict an output based on the inputs. And structured data usually comes from things such as relational databases like MySQL, Postgres, and other relational databases that allow us to do something called SQL queries. That is, to perform actions on these structured data to collect information. Then there's semi-structured data. There's still structured data, but often in something like an XML, CSV, which we've seen, or JSON form. And these are just different extensions and different ways to store data in different files. For example, a really popular website to grab data that's freely open online and find data sets, maybe even do competitions or see other people's notebooks and talk about machine learning topics. Well, Kaggle allows us to actually look at data sets that are available for us to use and play with. And in here, if I type something like XML, it'll give me all of the information or all the data, let's make this bigger, that are in XML format. So for example, if I click on blood cell images, and I take a look over here, I see that the data sources, there's some CSV files, but there's also some XML files. And if I scroll down, there's also some images as well. So different formats of data that we can use. By the way, if you click on filter here, you'll actually see some of the file types available for data. Now we know about CSVs. There's also JSON, where JSON, if we take a look, and let's go to this beer styles one. If I scroll down, we see that it's in JSON format, and JSON format, you can see, has this tree-like structure to explore data. So just a little bit different than CSV, just another way to organize data. Like I've mentioned, on Kaggle, you'll find all these types of data sets using different things. SQLite, for example, is a type of database and using SQL, so structured data. So if I do SQLite over here and search for something using relational databases, you'll see that this uses SQL. And it tells us what kind of columns it has. So lots of ways to explore Kaggle. But these two types of data are usually well organized and easy for us to manipulate with tools such as pandas for CSVs, and you can actually do SQL as well with pandas. The third kind is unstructured data. And Daniel has already mentioned this, right? This idea of an unstructured data are, well, they're not usually in simple formats that we can really manipulate and analyze easily. These are often things such as emails or PDFs or any sort of documents where perhaps actually understanding them is a little bit more difficult. It's unstructured. Finally, we have binary data. These are things such as audio files, image files, video files. They're in binary, that is ones and zeros that computers can understand, but for us to categorize them, that's really, really difficult. As you can see, it goes from top to bottom. From really organized, well-labeled data to something that is a little bit harder to organize, especially for machines. So why do we have to talk about these four types of data? Well, because most businesses, the bigger they get, aren't only going to have structured data. They're going to have all sorts of data, all sorts of inputs that needs to somehow all work together. So one of the jobs of a data engineer is to essentially use the fact that there's all these types of data and somehow combine them or organize them in a way that is useful to the business. Let's take a break here and explore some more in the next video. Okay, so what does a data engineer actually do? Let's start off with 3 big words that we need to understand before we really understand what a data engineer does. Yes, I know I keep circling around data engineer and I keep getting you excited, but I promise we're getting really, really close. We just need to discuss these 3 words that you may or may not have heard of. One is data mining. And data mining simply means pre-processing and extracting some knowledge from the data. So we use some sort of data to extract knowledge from. That's what data mining is. Big data? Well, it means we have a lot of data, a lot of variables, so much data, in fact, that you can't run on your laptop. There's just too much data for your laptop or computer to hold. Usually, when we talk about big data, it's data that's so big that you need to have it running on cloud computing or multiple computers, such as AWS, Azure, and Google Cloud, because they have a lot of computers and a lot of storage to store this data. So that's what big data is. Big data is data that you usually can't have just on one computer. This usually happens because, well, data sets get so big. We have petabytes and petabytes of data now. So just having data in a database like MySQL or Postgres or any type of database becomes really difficult when that database is just one single machine. Now, new technologies were invented to solve this problem of big data, like Hadoop and NoSQL, which we'll talk about. Now, a data pipeline is essentially a pipeline that a data engineer builds to essentially use the fact that we have this big amount of data. We need to extract information from this data using data mining. So we need to bring or build a pipeline that allows us to flow from that unknown large amount of data to a pipeline that extracts data to a more useful form. So a data engineer essentially does this, creates a data pipeline where all the information that different devices like IoT devices, mobile applications, web apps, cameras, cars, and pretty much anything that collects data and stores information or logs data into servers or to the cloud, a data engineer essentially accumulates all this information into nicely packed databases and storage engines so that different parts of the company can create visualizations. They can monitor the performance of their product. They can get business insights and make business decisions from this data, and even use this data on their apps, for example, for user profiles. Before a data scientist or a machine learning expert or even a business intelligence or data analyst gets hired, for a big company, the thing that they need to do before all of that can be done is to hire a data engineer. They build the pipeline that allows us to work as data scientists. Remember this diagram and how we've been focusing on this part? Well, a data engineer allows us to do this data collection part. They bring in all this information, organize it in a way for us to do our data modeling. They really help us with this data collection part that usually as a machine learning engineer or data scientist, you don't have to concern yourself too much with. But you know what? My favorite demonstration of what a data engineer is in the next video. I hope you're excited because things are going to start to make more and more sense. I'll see you in that one. Bye-bye. Okay, so in the previous video, we understood that a data engineer essentially creates this data pipeline for us, for people like data scientists to have available data to work with. But I want to use a different example. Let's pretend that Keiko Corp has a need, and that need is for water. The employees need water to work hard, right? So let's think of this as a problem that a data engineer solves. Now, bear with me. We're going to be talking about water for a few minutes, but I promise it relates to data. You see, the very first thing for us to get water is rain, right? We need rain. And this is similar to the data sources that we had. That is the websites, the mobile phones, the cameras, the cars, the drones. All of these are collecting data. That's what the raindrops are. So in order for us to get water to our employees, we have to get water from somewhere, and that water comes from rain. Next, that water gets collected into different streams and rivers from all over the place, right? From all over the world, just like data. From all different places, these streams of water start forming. And what happens next? Well, these streams of water turn into lakes. They all flow into some sort of a lake. And that lake kind of sits still. But again, we as a Keiko Corp just want water from employees. Well, we obviously have a dam on a lake, and that dam on a lake or a system to use that lake, well, we transport that water to something like a filtration sanitary area so that we can clean the water, sanitize it so it's safe for people to drink. So we process that water that has been collected. And then finally, after all of that, we create all the plumbing and pipes for us to deliver water to Keiko Corp. That's how we satisfy the needs of Keiko Corp to provide water for their employees. And this is how data works. And this is what a data engineer builds. A data engineer starts off with what we call data ingestion. That is acquiring data from various sources. And we acquire all these different sources of data and ingest it into what we call a data lake. A data lake is a collection of all this data into one location. From there, we could just leave the lake as it is. But there's a problem. We don't want the lake to overflow, dry up. We need to manage this lake somehow. We don't want to flood the village. We need dams. We need pipes to the houses. We need to filter and clean the water. And we need piping to the houses. So after we ingest this data from various sources, we collect it in a data lake. We then perform something called data transformation. That is converting data from one format to another, usually into something we call a data warehouse. A data warehouse is a place that stores accessible data that is useful for the business. That is, although the lake collected so much water, so much data that was kind of all over the place, a data engineer looks at this data and forms or uses the parts of the data that are useful and puts it in a data warehouse so that other parts of the business can use it. Again, a good way to think about it is that a data lake is a pool of raw data, the purpose of which we still don't know what to do with, and a data warehouse is a location for structured, filtered data that has been processed and has a specific purpose. That is, we have data in here that is useful for the business. So that means that data lakes are usually less organized and has less filtration of data than something like a data warehouse. Now, why would businesses want to do that? Well, for one, it's a lot easier to analyze data when it's organized well. We also might have data in here that we don't really need. We also save on storage space, right? Because we don't have to store all of this data and just store structured data only that is only useful to us. We also save ourselves some money. So to review, a data engineer simply builds this pipeline of taking the data creation and data capture, using data engineering practices to build this pipeline so that data can now be analyzed by data scientists and data analysts. But we still have a little bit more to go. So I'll see you in the next video. Welcome back. So we just went through this whole flow of how data is used by a company. But there's a few more things I want to talk about, because right now we just talked about water and how does this really apply? What kind of tools do data engineers actually use? Well, you may have heard of something like Kafka. And we'll get to Kafka later on, but something like collecting these data streams and putting them into a data lake might be something that Kafka or Apache Kafka might do. For data lakes, for example, these are simply programs that companies can use. For example, you may have heard of Hadoop or Amazon S3 or the Azure Data Lake. These are programs that have been built by engineers to hold large amounts of data, like a data lake. And then for a data warehouse, we have tools like Google BigQuery, Amazon Redshift, even Amazon Athena. These are data warehouses that allow engineers to make queries or analyze this structured data. Now, I know what you're thinking. Who does what in this whole system? We've learned that the data engineer creates this entire system for us. They use different tools and programs to ingest data and then put it into a data lake or a data warehouse. So as a data scientist and a machine learning expert, which data do you use? Pause the video and think about it. Ready for the answer? Well, most of the time, you'd be working with a data lake. Because remember, if you're doing machine learning, the more data you have, the better, right? And with machine learning, you can use structured or unstructured data. So you can go into a data lake and actually grab a bunch of data to use for your models, whether they're in CSV forms or any other forms. And usually, data warehouses are used by BIs or business intelligent people or business analysts or data analysts to make visualization or analyze data. Because the data warehouse has usually more structured data that has been cleaned out than it was when it was a data lake, it's a lot easier to understand and use the data for information. Now, as a data scientist, you can use the data from a data warehouse. And this isn't just a rule. It's usually you use whatever data is usable to you. But this is a good way to think about things, that a data scientist uses as much data that they can, as much useful data as they can. While somebody like a business intelligence person or a data analyst has already the data cleaned, processed by a data engineer and use something like a data warehouse to analyze data. And Google's BigQuery is exactly that. It allows somebody with not too much engineering experience or programming experience to analyze this data in a data warehouse. Another way to think about it is like this. Usually, a software engineer, a software developer, app developer, mobile developer, they build programs and apps that users and customers use, and that releases data. Then, a data engineer would build this piping and pipeline for us to ingest data and store it in different services like Hadoop, like Google BigQuery, so that that data can be accessed by the rest of the business. Next, we have data scientists that use the data lake as well as the data scientists to extract information and deliver some sort of business value. Finally, we have data analysts or business intelligence to use something like a data warehouse or structured data to again derive business value. And I hope that clears the picture a little bit when you hear all these titles out there in the industry. Now, the industry is fast evolving, And there's definitely some overlap, and sometimes what one job description might say might be different than the other, but these are general simplified rules that you can use to understand how each role plays into the part of a company. Let's finish up this high-level overview of what a data engineer does by describing the three main tasks that they do. One is that they build what we call an ETL pipeline, or an extract, transform, load pipeline. So unlike data ingestion, which simply means moving data from one place to another, an ETL pipeline is the idea that a data engineer extracts data that has been generated by all of these systems. They extract that data, and then when they extract that data, they transform the data into a useful form. That is, into a form that can be loaded into a data warehouse. So they extract the data, they transform the data, and they load it into something like a data warehouse so that the data can be used by the rest of the company. And they use programming languages like Python, Go, Scala, and Java to accomplish these ETL jobs, or extract, transform, load. So that's the first task. What's the second one? The second one is building analysis tools. You see, for us to understand how our company systems work, a data engineer needs to make sure that when any part of the system breaks, we are notified. So a data engineer allows data scientists, data analysts, business intelligence people to use tools to analyze the data, but also to make sure that the system that they've put in place is running correctly. Finally, their third main task is obviously to maintain the data warehouse and data lakes. That is, making sure that everything in there is accessible for other parts of the companies to use. So now that we have a high-level overview of what a data engineer does, I want to talk about some of the tools that you have definitely heard of in the industry. Things like Hadoop, Kafka, Apache Spark, all these terms that are really hard to understand. I'm going to try and give you an overview of this landscape so that next time when somebody asks you, hey, should we use Hadoop? Hey, what's Hadoop for? Do we need Kafka? You'll be able to answer that. And after this course, you can go off on your own and actually learn to use these tools if they ever come across in your job. Now, this landscape is fast changing. There's new tools popping up left, right, and center. So my advice to you is that what I'm going to show you over the next couple of videos, you don't take as the absolute must know for all data engineers. Instead, know that they exist. Go and read some of their documentation, some of the information online, but only learn or use them once the need arises. Because they're constantly being updated, and the world of data engineering is really fast-paced right now. But with that said, let's nerd out on data in the next couple of videos. Welcome back. Let's talk about the types of databases that exist. Now, here's the thing. The world of databases is extremely complicated. There's so many databases out there, so many new innovations, different databases for different things. It's impossible to know all of them. So we're just going to do a brief overview of what exists and why we have so many databases. So let's start off with the first one. Why do we have so many databases? I mean, look at this little diagram that I found. That is a lot. Well, because we have different needs with data, different databases are good at different things. So there's many different databases because we need them from different solutions. But the first thing we need to talk about when talking about databases is this idea. There's three main categories of databases. Now remember, databases are just computers. They're computers with a hard drive, essentially. Just like your computers is able to store files and have files available anytime, that's what a database is. Every time you turn off your computer and turn it back on, you expect your files to be there. And a database is that. you expect that your data persists. That is, the data that you save, whether we turn off the computer or turn it back on, it's still going to be there, and then we can access it, we can modify it. That's the role of a database. And we have three main types. One was the original type of database, which was relational database. A relational database is a database like Postgres or MySQL that allow you to use SQL to make transactions. That is, to write to the database, to read to the database using the SQL language. Now, relational databases were all great until around 2000s, when initially we just had one database, one master database that held all the information that we needed. But starting in the 2000s, we got more and more data. We collected more and more data, and all of a sudden, all that information cannot be stored on just one database. So we had an issue. We now needed two databases to hold that information. And although I'm simplifying things, the idea was that now because we need distributed databases, that is, we needed more than one database to store all that data, relational databases didn't have the necessary tools to have this idea of multiple databases working together. So NoSQL databases were born out of that. Databases like MongoDB became popular because for the first time, it allowed us to do distributed databases. That is, we can have different machines, 10, 15 machines, all working together as one database. Finally, more recently, we have this idea of a new SQL database. What does that mean? Well, new SQL databases are still fairly new, but they try to get the best of both worlds. You see, relational databases are really, really good for something called ACID transactions. They have some really nice guarantees when we read and write data to make sure that it's always accurate. NoSQL databases were a little bit more disorganized, but it allows us to store information on distributed databases. That is, as our data gets bigger and bigger, we can have a NoSQL database on different machines so that it scales up with our data. New SQL databases like VaultDB or CockroachDB are trying to have the distributed nature of NoSQL databases so we can scale up our data, but also have some of the guarantees of relational databases. Now, these new SQLs are still in the works, but definitely keep an eye on them. Another way to talk about databases is using databases for their own specific needs. For example, there's some data storage or databases that are specifically used for searches. For example, Elasticsearch or Solr are used as searching databases. So we put data in there and it allows us to search for things really fast. Then we have things like computational databases. Something like Apache Spark that allows us to use the data that we have in the database and make computations and calculations on them. And we'll get to Apache Spark shortly. Finally, I just want to introduce you these terms that you might hear when it comes to data engineering. OLTP and OLAP. You can think of OLTP databases as relational databases or SQL databases that allows us to make transactions. For example, if you have a web app, and that web app has a user that you can store user information, you can upload photos, and have that application interact with a database for a user, that's OLTP databases. An OLAP database is usually used for analytical purposes. Now, I'll leave some resources if you want to really dive deep into this topic. But as you can see, there's many ways to describe databases. We have many different types of databases, but at the end of the day, each database is good for its own specific use. If we look back at our diagram, databases are used everywhere. For example, these streams, these are usually OLTP databases, like relational databases that collect information. Let's say a user on a mobile phone updates their username, well, that goes to a relational database, an OLTP database. And then a data lake, well, a data lake is another database. usually something like Hadoop, which we're going to talk about. And then that data goes into a data warehouse. All of these things that we see here are essentially databases. We collect information from different streams. We have data lakes, which are databases, and data warehouses, which are databases. So over the next couple of videos, knowing what we know about databases and how we have different types of databases, let's try and figure out how this whole picture of a data engineer works. All companies store data. From a simple record book of a small business, maybe even on a journal or a piece of paper, to massive companies like Amazon that need computers to store petabytes of data. Now, in order to store this information, pretty much every company, and sometimes individuals too, need something called a database. We saw in the last section how hard it was to have our server remember a new user. Every time the server crashed, the variable would get reset and then it would start all over. Or if we wanted to do a login or a sign-in check and iterate through the emails and passwords, doing a loop through JavaScript, that's inefficient. That's where databases come to the rescue. So let's ask ourselves, what is a database? A database is a collection of data. And what we mean by data, there are many forms of them, right? There can be numbers, there can be dates, there could be password hashes, there could be user information. Databases allow us to organize this data in a way that is useful to us. And it makes data management easy. And something came out of that. And it's called Database Management System, or DBMS for short. It's a collection of programs which allows us to access databases and work with data. And it also allows control access to database users. So a DBMS is something in this box. Something that allows us a tool, a piece of software that allows us to communicate with the database, store information that's useful for us, and also allows us to update, insert, delete, look up, whatever is in the database. And this idea of a DBMS really started to take shape in 1960s. And now it is at the forefront of many exciting things. There's an entire industry of engineers that just work with databases because it is so important. Now, there are two types of DBMS that are really popular right now and that we're going to talk about in this course. And these two types are represented really well by Postgres and MongoDB. Let's talk about the first one, which is relational database. And this is probably the most popular. As you can see on the right-hand side, you see that all of these are relational databases. Postgres, Oracle, SQL Server, you may have heard of MySQL, SQLite. These are all types of databases that have this relational database tag to them. And the beauty with them is that they're all pretty much similar. They all follow a same standard format. Relational databases consist of two or more tables with columns and rows. So in this case, users is a table, and full name, username, text created at are columns, and whatever values they have here are rows. Each row represents an entry, and each column sorts a very specific type of information, like name, address, or phone numbers. And then the relation between tables and fields is called a schema. In a relational database, the schema must be clearly defined before any information can be added. And if this is confusing right now, don't worry, we're actually going to create these databases so it makes sense to you. If we had Twitter, for example, you can see over here the types of tables that we would have and how we would organize it. We would have a users table, a tweets table, a following table. And we can connect all these information, for example, by connecting different pieces of the table. For example, the username will be the same in the users table as it is in the tweets table. That way, we can say that the username in the tweets table is the foreign key of the username in the users table. And then from user will be the foreign key of username in the following table. Now, things like full name or ID, something that identifies each row in a table, is called a primary key. And we'll go through that later on in the section. All right, so all these databases, we're going to learn about PostgreSQL, but they're all pretty much the same. So once you know one, it's fairly easy to pick up the other ones. How do they actually communicate with a server, with the backend? Well, all relational databases use something called SQL. And SQL allows us to communicate, just like HTTP did, between the front end and the back end. With SQL, we're able to communicate with the database and modify or get or update however we want. And we'll have a video on this topic as well. All right, so that's relational databases. What about the second type? The second type is called a non-relational database or a NoSQL database. And once again, there are many, many different types of databases with some cool names like CouchDB and Hypertable. Now, a MongoDB or a non-relational database lets you build an application without having to define the schema first, unlike a relational database. If we go back to relational database, this schema or these tables have to kind of be predefined, right? We need to know how our app is going to look, make these tables so that once the app is public, we can start entering user information and tweets and followers. With a NoSQL or non-relational database, we can just define it as we go. And they all have different ways of storing this information. So each one is very, very different. And this is another powerful reason to use a non-relational database, is that if your data requirements aren't clear at the outset of your project, and maybe you have a massive amount of unstructured data, you may not have the luxury of developing a relational database with a clearly defined schema. They offer instead a greater flexibility in that a non-relational database are more like folders, just assembling related information of all types. Now, MongoDB is something called document-oriented. It stores information as documents. Let me illustrate this point to you. I have my desktop here with two folders. One is a relational database, and here I have users, tweets, profile, following. And you can think of relational databases with this type of storage, where this folder lives somewhere on a computer that stores this information. And anytime we need to ask a database for something, well, we grab the users. And if we also want to grab the tweets of the user, we find the user that we're interested in, then find the tweets of the user that we're also interested in with the foreign key that links to the users. And we can also find however many followers that user has. We grab that information and display it on our web app. MongoDB, on the other hand, will actually have each user as a document. So if I wanted to grab the first user, well, I just grab this document and it has all the followers, the tweets, the profile, everything is in this one document. And you might be thinking, MongoDB looks like a better choice than having this way of doing things, right? Well, it depends on your need. And that's why databases is such a complex topic. It really, really depends on your situation. You can see this MongoDB way being very useful if you had something like a profile, maybe a LinkedIn profile. But if you needed something where you're working with just following data or just tweets data, maybe with the tweets, you want to see what is the average tweet size. Well, it's really easy to just grab this file and calculate that versus this way where you might have to extract it from each one of the users. So it really depends on your needs. Let me show you another diagram that might be useful. When we look at relational versus non-relational databases, you can think of relational as each table has a blog post, a blog tag, a blog comment, and it links these tables to give you the blog information. Versus a non-relational that stores this entire blog post in an entry and has comments, tags, categories, and all other related data just in one single place. So what does MongoDB use to communicate? If we go back to our example here, we had SQL for relational databases such as Postgres. Well, MongoDB has its own what we call query language. And it is just the MongoDB query language. But they both aim to do the same thing. That is to communicate with the database, provide an easy way for the server to communicate with the database. And in this section, we're going to be talking about that. And we're going to finally connect the dots and show you the power of databases once they're connected to a server. I'll see you in the next one. Bye-bye. Let's talk about Hadoop. So as companies started to generate more and more data, our databases that we had, like MySQL, became too inefficient or unable to hold the large amounts of data. And Hadoop became a cornerstone of data engineering. You see, Hadoop is an open source distributed processing framework. It allows us to do data processing and storage for big data. And it was actually developed by Yahoo back in the day, and then later donated to the Apache Software Foundation. Hadoop was all the rage when the big data craze started. Hadoop was a solution that allowed all these companies with petabytes of data to store this information in Hadoop. Now, Hadoop was essentially a data lake, right? It's a data lake solution. It allows us to just store all this data for us. But the popularity of Hadoop was because of two big things. One was HDFS. That is the Hadoop Distributed File System. Hadoop was able to store so much data because of this HDFS, a file system, just like you have on your computer, that allowed it to store files on multiple computers. That is, we can use Hadoop on multiple computers to store as much data as we want. It was scalable. We could scale out. So data is stored across different physical computers. Then was MapReduce, because once we store data, we need to perform some jobs, some processing on that data, right? And MapReduce in Hadoop allowed us to perform jobs against this data that we had in a data lake. Using languages like Java or Python, you can use MapReduce in Hadoop to do what we call batch processing. That is, every night we can run some sort of a job to clean our data, to process our data, and make it useful for the company. Now, MapReduce isn't used as often anymore, as we'll see later on in the videos, because we have something called Apache Spark. That's actually a little bit faster, but we'll get to that. The idea here is that we finally had a tool with Hadoop that allows us to store a lot of data across multiple machines using the HDFS and run batch jobs using MapReduce on this large sets of data. And a lot of other tools started popping up around Hadoop. Tools such as Hive. Love their logo, by the way. Check that out. Anyway, Hive makes your Hadoop cluster feel like it's a relational database. Even though it isn't, it allows you to use Hive and write SQL queries against your HDFS file system. So in a sense, you kind of had this data lake of Hadoop and also a little bit of a data warehouse type thing with Hive by allowing SQL commands on your data that hopefully was processed using MapReduce. And you may not have heard of Hadoop before because it's used by data engineers. Remember, data engineers usually don't work on systems that are customer facing. That is, they don't build databases that you would use with your app or with a web app. Instead, they build the systems behind the scenes that ingests, collects, runs ETL jobs, that is extract, transform, load on data. So Hadoop is that behind the scenes storage layer that stores large amount of data running batch processing against this data so that we can have some useful information. And Hadoop is still very popular and very capable when it comes to large data, petabytes of data. Let's learn a few more tools in the next video. Let's talk about Apache Spark and Apache Flink. You see, before Apache Spark, usually people used Hadoop MapReduce to process everything. Spark came along and actually improved the MapReduce in Hadoop by doing something called in-memory processing, which essentially allowed Spark to run processing jobs much faster than MapReduce. So Apache Spark became really popular. And it's probably the go-to batch processing framework. So if you want to process a lot of data, well, you can use Hadoop to store that data in HDFS and use Apache Spark to run ETL jobs like extract, transform, load to clean and transform that data. Now, up until now, we had batch processing, which essentially means give me a chunk of data and I'll process this data over a bit of time. Usually, you'd run a batch processing job at the end of the night, and in the morning, after a couple hours, the job is done. But as of a few years ago, the idea of real-time processing started to happen. Things like Spark streaming came out, which almost made real-time processing possible. That is, instead of batch processing where you waited until the end of the night to run some jobs on an amount of data, instead, every time data comes in, you process that data. In this space, Apache Flink really took on the charge. It offers real-time stream processing. Now, although Spark is still popular, tools like Apache Flink are starting to become popular. Now, this idea of streaming data and stream processing is becoming more and more popular. It's still new, but there's some exciting things happening in this landscape, so let's talk about that in the next video. Welcome back. So we learned that as a data engineer, you collect data, you ingest data, and then you store it in a data lake, often a Hadoop cluster. Now, this idea of a data lake can also be used with something like AWS's S3 object storage. So those are the two most popular ones. And then once they're in your data lake, you can usually run batch jobs on this data to clean it up or modify it or wrangle it in some way. So Hadoop allowed us to do that with MapReduce. We can use Apache Spark. You can just manually write scripts on Amazon S3, or you can just even do batch jobs with common databases like SQL databases. But this idea of stream processing is now becoming more and more popular. Instead of processing data using just batch jobs, let's say every hour or every day, there's now a movement towards this idea of real-time stream processing. That means when data is received, processing it right away instead of waiting a bit until we can do batches at a time. This allows us to have faster reactions to data. Now, this idea of stream processing is pretty complicated, but one of the main tools that's being used right now for stream processing is something called Kafka. Kafka, if we look on their website, is a distributed streaming platform. It allows us to read and write streams of data like messaging system. It allows us to process, and it allows us to store data as well. But as you can see, what Kafka does, it allows us to receive messages and pass it on to different places. So what you'll often see is we use Apache Kafka to receive all these messages, logs, and data from all these sources. We collect them in a central location, and then Kafka can pass it on to different locations. For example, we can pass off whatever Kafka receives to a Hadoop cluster to store that data, and then perhaps, if we want, use Apache Spark to process that data into a data warehouse. But now with the idea of real-time processing, Kafka allows us to now pass things on to, well, itself, or we can use something like Spark streaming, or Flink, which we've talked about, Apache Flink, that is used more for stream processing, or Apache Storm, or even Kinesis by Amazon, which actually can also be placed like Kafka here to handle all these messages from all these locations. Now, at the end of the day, all of this might have been confusing. You may be overwhelmed by all of these tools that are available. But remember what I said at the beginning of this section. A data engineer is somebody that you'll interact with as a data scientist. So it's good to know what they do, what their roles are, what their responsibilities are, and you'll work closely with them for you to have the data available to perform analysis on it or build machine learning models. But I hope that this diagram now makes sense. A data engineer creates this landscape for you, where they ingest data through Kafka, store information using something like Hadoop or Amazon S3. They process that data using something like Apache Spark or Kinesis. And then they even store data in data warehouses, so tools like Redshift or BigQuery can be used by people inside the business to learn something useful from the data. They build the structure for you to flourish. So be nice to them. And if you're ever interested in any of these technologies, they're changing very fast, but they're definitely worth a look, and they're not as intimidating to learn as you might think. I'll see you in the next one. Bye-bye.